Hello everyone! In this video, we will continue to look at the phenomenon of single-slit diffraction. In particular, we will examine the application and skills of qualitatively describing single-slit diffraction patterns produced from white light and from a range of monochromatic light frequencies, as well as X-ray diffraction. We will conclude with an example. A quick reminder that the formula derived last time for single-slit diffraction gives the angle between the central maximum and primary minimum as a function of the wavelength of the incident light and the width of that single slit. So our question is, what happens when white or non-monochromatic light is shown on a slit, on a single slit? What you get is shown right here. So with green laser light, you can see that characteristic central maximum right in the middle there, as well as secondary and tertiary maxima, as well as the primary minimum, okay, that first point of destructive interference. And we can see that for white light, you as well get sort of that a pretty intense white central maximum, as all of the wavelengths of light more or less line up along one another, but you also get a rainbow effect in the secondary and tertiary maxima. And that's because the angle of the primary minimum, okay, the angle of the primary minimum depends on the wavelength. We saw that theta is equal to lambda over b, and so if you have a higher wavelength, lambda, you expect a higher theta. Okay, what that means is that the diffractive effect is bigger for larger wavelength light. Because red light has a larger wavelength than blue light, you can see here that the red light for that primary, or that secondary maximum is at a larger angle than the blue light for the same secondary maxima. And as a result, you get sort of a rainbow effect in those fringes. You can also see that the edge of that white central maximum, right here, is more red than it is blue. And that's because if you see this curve right in here, that blue curve falls off. So this is a graph of the intensity as a function of wavelength, although for whatever reason, the makers of this particular graph did not color those curves appropriately, but we can do that for them. So we can say, oh, well, this outermost curve right here has a larger angle, okay, larger angle. It meets this axis for the primary minimum at a larger angle than the other curves. As a result, it must be redder. So we'll go ahead and call that particular line red light. And then the other wavelengths would be along the spectrum. So this would be yellow. This red line would be perhaps green. And this innermost blue line would remain blue or violet. Okay. All right. So given that, we ask one more question, which is, what would you get if instead of a single slit, where this is the pattern we see on the back, you had a circular aperture? Okay, so with a single slit, our equation is theta equals lambda over b. But with a circular aperture, it's as if you took that entire pattern and you just sort of rotated it around, okay? And you get something that looks like this. And as it turns out, that angle is slightly different for a circular aperture for reasons that I'm not going to go into that have to do with the sort of geometry and trigonometry of the problem. But the only difference is that theta is about equal to 1.22 lambda over b, and that's just an extra factor there, okay? And so this would be the intensity pattern for a circular aperture. You can imagine light going through a very, very small hole rather than through a small slit. You would see this characteristic diffraction pattern. This can be seen in this lovely simulation at FET. Okay, this is the wave interference simulation, and if I refresh the page, I can choose many different options. It's excellent for showing single slit diffraction, for example, right here, with a particular wavelength of light. We could see how that intensity graph is made, and what that phenomena would look like if we play with these parameters here. We increase our slit width. Okay, that will decrease that angle. And as a result, you can see a very distinct single slit diffraction pattern on the simulation. The simulation also allows us to view what would happen for a circular aperture. And you can see here that if we have a particular object, we can use diffraction, all right, with different wavelengths. You can imagine measuring the size of that small object, like so. I'll just play with those parameters a little bit. You're welcome and encouraged to pause the video at this point and take a minute just to play around with the simulation. The important ingredient, though, is that this phenomena can be used to measure crystals, in particular in a process called X-ray crystallography. So instead of with visible light, you shine X-rays at a crystal. A crystal has a structure that looks a little bit like this grid right in the middle here. And from that diffraction pattern, using those X-rays, you can determine the distance between the atoms in the crystal, and you can determine the structure of the atoms. So you can actually use diffraction to figure out sort of the intermolecular structure of a crystal, which is pretty cool.